Do you want us to turn it in now or later?
Oh, you could turn it. You could turn it in whenever.
Oh, okay. Just whatever's easier. I think maybe during the break might be easier. Okay. Yeah.
All right. Well, I've got some a little bit of classwork for you here. Here. And you will need a calculator for the first question at least.
Thank you. I see. So this is for air.
And while you're busy on that, I'm going to go grab my notebook because I left it in my office. So I'll be right back. Did y'all have a chance to look at the video that I posted? Yeah, I'm sorry I posted that so late. In the ideal world, I would have posted that at the beginning of the homework, but I just am so struggling to keep up that I'm just behind on everything. So I thought better post it sometime than never. So I hope that it helped. At least the ductulator video on how to use the ductulator appropriately. I actually made some video last year for that, and I couldn't find my video. I thought it was on YouTube somewhere, but YouTube did something over the summer where they required you to, if you had really old stuff, you had to go in and basically re-upload it, or it became invisible to viewers couldn't access it. And I lost some of actually quite a lot of my older videos because of that. It's really frustrating. So I'm remaking some video that I used to have. And the fan distribution example, I tried to include both the equivalent length method and the loss coefficient method. And in that example, you can see that for fittings that have like a T, or we can have a T fitting. We can have fittings like this. And I mean these are diverging. That's a diverging Y, but you can also have a converging Y. And with all these fittings, there are losses associated with each of the strings typically, or at least with if your inlet is here, there's going to be a loss coming out of both sides. And if we have the loss coefficient method, we typically will have a loss coefficient for the branch and a loss coefficient for the straight through section. So we're doing, and we'll take this loss into account when we're studying this segment, and we take the branch loss into account when we're doing that segment. In the example that the homework problem, you just had an equivalent length, and if you have the equivalent length for the fitting, you only use that once. And typically for a T fitting, you use that on the straight through segment. Yes, sir.
So for this last one,
Yeah.
on question 1, part A, where
Yeah.
you ask for the air velocity, you need to say feet per minute instead of feet per minute.
Oh, 1A, the air velocity, yes, feet per minute. Sorry about that. That's feet per minute.
We have two questions
Yes.
about that. So if the inlet was actually on the top and split towards the sides, would we use equivalent length for both of them? Or is it a different equivalent length that we should be looking at?
If the flow rate is, so it's just like this,
Yes.
yeah, then it would be different.
Right. And when we're looking at these diagrams, what you just said implies that we should actually take the branching literally. Like if it goes straight, that's actually the string, and the other is the branch.
Yes. Yeah.
I didn't do that.
Yeah, and when we represent the airflow system, we should try to represent the branches as they really are. So if we have a 90-degree branch, it would look like that. If we have sometimes we have a 45-degree that goes like that.
That seems like it can get pretty messy with some systems, but you keep on needing to make right turns. Do they ever deviate from that and annotate it like this is not actually oriented how it is on the diagram?
No, because the diagram has to be used by the contractor, who actually installs, so they have to know the angles, elevations. So you'll have, you have an elevation diagram to show the ductwork from floor level, assembly level, but then you also have the, what do you call that?
Overhead.
The overhead. So that, yeah, you have to work with both of those. And, yeah, those are done to scale, just like, using SolidWorks. But I think you can do ductwork design in SolidWorks, I think. But there are systems that are more tailored to HVAC design. So yeah, you have to rough in your ductwork, and then your piping goes around that. So it can get pretty busy. But typically, you have the whole system diagram, which is the P&ID, and then you'll have subsystems. You'll have diagrams for some parts of it that will have more detail. Yeah. But yeah, the fittings or losses are just awkward to work with because this is all in software now, and when I do this, I just dial in my fitting, and it automatically does the loss calculations for me. So I'm trying to remember, how do I do this by hand? And it's actually quite cumbersome to do by hand because you have to calculate these are not given. These are based on characteristics of the piece of duct itself. So you have to go and look for a T fitting, and it's a full flow T fitting versus a T fitting where one section is the pipe is much smaller than the other. But there are standard fittings, and you look them up, and then and I think they have some in our book at the end of the chapter, and they'll actually tell you how to calculate these loss coefficients. But to calculate them, you need to know it's based on the diameter of the duct and the velocities at different points. So you may have to know the feet per minute coming in, feet per minute going out. And if it's an elbow, we have to know the radius. So there's a radius of the turn, and typically we have to use we look at the ratio of the radius of the turn to the diameter of the duct. And so just to get one of these loss coefficients, you might have to do several calculations and then add correction factors on top of that. So it can be quite time-consuming and really quite a hassle just to figure out the loss in one piece of ductwork, or one fitting. So you can imagine, pity the poor engineers before computers that had to do all of this by hand. And now you can just dial in the duct into the ASHRAE. The ASHRAE has something like 250 standard ducts, and those are programmed into all the major HVAC design software platforms, and you just dial in which duct you need, in your flow rate, and it will do all this automatically for you. So you'll be spared having to mess around with this garbage. You still may have to deal with, I mean, this is fittings in the duct work, but things like filters and the outlets, you may have to deal with separately based on the manufacturer of that particular filter or the outlet. And they'll have tables that will tell you what the head loss is through that. And typically, these will be an equivalent length. So you just find out what the equivalent length is and add it to the length of your straight duct. But we really, I mean, using equivalent length, I shouldn't have done that. I was trying to find a way to ease the load of working with the losses and fittings, and getting back to an approach that I used to use a long time ago. And it didn't even tell you what the dimensions were. Somebody asked me, is the equivalent length table, are those in inches or feet? What's the unit of the equivalent length? And I went and looked at it. God, there's no unit listed. And of course it's feet, but this is part of the problem at HVAC is there's just all these assumptions about units. Okay. It's a lot easier with water flow just because fittings are standard. It's easier to calculate fitting,
Okay.
or to incorporate fitting loss into our calculation.
Oh, okay.
Yes.
Over here in the analog world. Yeah.
And just also want to mention that next week we're going to have two guests coming into class. Tuesday, FSI Engineers is a Seattle-based mechanical consulting firm, and it's a group that I know very well. And the guy's name is Ola Jarva. Last name, he's Swedish, but Ola. I just know he's Ola. But he's coming. I think his partner is coming in as well, and they're going to talk about what it's like to work as an HVAC design consultant and profile actually some of their work, some of their design work in the area. So you get a sense to see what how engineers are actually applying this stuff out in the real world. And then this is going to be an in-person visit. And Thursday, someone from AV Engineering, which is another mechanical consulting, they're quite large. FSI is pretty much local. I think they may have one other operation in Baltimore, but AB is pretty big company. And someone from there will be visiting us by Zoom to talk about what they do. And I've asked her to talk about what they look for when they're hiring engineers to work as in consulting, mechanical consulting. So that's the woman here, very active in ASHRAE, and she's a person who often I talk with about, what are you looking for in your graduates, and what can we do to better prepare our students. And, so I think you'll find it very interesting to hear what she's looking for. And, she also hires our graduates, which I like to see. I always like people that, not just interview our graduates, but actually hire them. Yeah. And I know FSI is looking at some of our students for internships. I don't know if anyone's actually, they're pretty small. I don't think they do a whole lot of hiring, but they do bring on interns, and I think they're looking at one of our juniors now. I don't know what's going on.
So are they coming to the class? Are they coming to the class?
Yes.
But our class is Monday, Wednesday.
Oh, sorry about that. Yeah, I mean, that would be a disaster, wouldn't it? Yeah, they come here, they're all set up on Tuesday and nobody's here. Yeah, Monday, Wednesday. 9th, today is, yeah. Then the week after that, one of our former students is coming, who's a project engineer at a local HVAC. I think he's in Woodinville. And he's going to talk about project management in the context of HVAC work. And he took this class the first time we taught it, so it'll be interesting to see. And it'll be the first time that I've actually seen him in person since he graduated.
Well, that's great.
Try to get my former student books for certified green buildings, see if he can come in working. He'd be a good person to talk to about codes and sustainability. He's into like building the sort of moving back to natural materials buildings.
I didn't bring my notes.
What?
I didn't bring my notes.
Oh, okay.
Which should you use for A?
For A, you just use the ductilator.
Oh.
So you have to look up what your friction loss is. So he says it's 0.1, so you turn it till you have 20,000 CFM at 0.1. And then you read off what your velocity and your duct diameter are.
Dynamic, high energy.
Yeah, that's what you're doing. So you've got to turn it. You do.
Kind of like.
So you're at 0.1. This is supposed to go to 20,000. So do 0.1. And then you go right here, so 20,000, and then you read off your. At 20,000, you read off your velocity, so it's 1,900 feet per minute. And then if you read off your diameter, it's 44 inches.
We're talking about 1994, 1995, something like that. So he's one of the first students. In fact, I think he's the oldest student that I've been able to maintain contact with. And I lost touch with him in the late 90s. He's Japanese. He studied Japanese American. He spent a lot of time in Japan, so he kind of has a connection. And he graduated and lost touch with him. 5 years ago. He's basically
You're assuming constant
project with
everything.
building an organization that certifies buildings. Not my student, but some other organization. And he sponsored projects systems engineer calls it. The students didn't know how to do it. He was kind of, not really the students, and he like talked down to them. And,
Then how did you find
yeah, so I did
It's
work
1900?
yeah. Also, the students complained about it.
How did you find this one in 1900?
Building codes, it's like, you know,
You did it on
there's
this?
something just come out and say, I'm interested in building codes. Yeah, it's not engineering stuff. We do building code. But, yeah, so when I was working with that guy,
So how did you find this?
You just read off where that 20,000 or 20,000 CFM, you read off. Yeah, you read off what it is here. So it's like, and then you read off what your diameter is
I
at
was
that
walking
point.
down the street and his friend, Tadashi, and he works with a certain thing, Tadashi. I used to know a Tadashi. And it can't be him, because he was a arts and sciences, not a technical. And it turned out that he was my former student, Tadashi Shino. He was doing the building certification. And I couldn't imagine working in that field. And but that's what happened. I just happened to find out about him and contacted him. And it was the same one. Back in the 1980s. This is like 4 or 5 years ago. Yeah, and then I nominated him for Distinguished Alumni. IAS as a Distinguished Alumni. When I learned about what he did,
44.
he won. And that was really cool. So they had this dinner and he and his wife and celebration.
That's it, right?
What?
That's it.
Do they pick
Yeah,
one person?
for A.
They do. I think they actually picked everybody. I haven't been
Last
on
we just look at the depth. For which one? For the last one?
For B, no. You have to use this equation. You just plug in the 1900 part, because it's 1900 divided by 4,005. And you square that, and it's certain blocks, so that's what I have the answers for the number students. For this problem, you just text one to check. Okay, well, you get the first one like 1,900 feet from there. Yeah, okay. And then for velocity, or for the velocity head, did you get like 0.225? Yeah, and then the one I got like 56.
Yeah, just got things in the ballpark.
Oh yeah, because you're using the algorithm, right? Yeah.
You got better things to do than
Brake horsepower. Does it give you brake horsepower? Brake horsepower is air horsepower divided by the efficiency. So you rearrange the equation to solve for N. So, yeah, I can just, if you want, you can just look at it. I don't mind.
I don't like writing stuff like that.
You just gotta copy and paste from years before, you know?
Just, yeah, copy paste, but, yeah, it's really time consuming to do that. Which I think you shouldn't have to do. Other people should do that for you. You shouldn't do that yourself. Because anybody can just, I'm great because I work 8 hours a week and sleep 3 hours a night.
So that's a unit, right? So that's a unit, right? That's a unit.
Yeah, CFM, and then, yeah.
I thought you multiplied.
No, I just have it where I write it out, because that's what he
Probably
calls
still too early.
in the notes.
Somebody.
What year did the program open?
Did you get that?
The NE program?
The program, that's one of the newest. I started in 20.
Most definitely.
Fall of 20. I think our first graduates were 2016. Well, 8 years since I started. Fall of 2014.
That's a unitless, right?
Okay, vigorously. What?
They need to plug in 18 on the bottom. You gotta plug in.
Oh, okay.
You plug 18 in on the bottom. Well, actually, you won't do it there. Your efficiency will be here. So at a race, it's your efficiency is This is the equation for brake horsepower. If you solve for efficiency, then you swap. Yeah. So brake horsepower, you'd actually have efficiency.
Oh, that's right.
It wouldn't be brake horsepower.
I never was able to like get past like the research.
Yeah. So this is the brake horsepower equation. That's the.
Spoiler alert. Somebody, one of her founders is like interested in geothermal.
That'd be nice. Yeah, I think they're really into that, and they're in a good location for it.
Just kind of waiting for Kelly to respond back to me, but she said that she's really busy this week and the next week. So.
That's very simple.
Oh, I was basically saying,
Yeah, she's like back to me. I messaged her on Friday. Well, I messaged her Friday, then she responded on Friday. I wasn't able to respond until Saturday. And usually nobody responds on weekends.
Yeah, I know she does.
could do it with question and then she could be, I mean, this is the same, I just use this.
But, yeah, just keep pushing. If you let me know here. So, I'll see if I can get you in touch with Josh. He spoke as a citizen engineer last year. And he was going to therefore students welcome. Even though he's not an engineer. So, for this year, we didn't really talk about buildings.
Which one did you use?
E
Did you get 5.8?
Did you get an answer for any of them yet?
Yeah. I think we did.
You're all done? Yeah, let's, why don't we, let's see, I can, well,
Isn't that the?
I need more space up here.
I can move my stuff if you want to put something over here. I don't mind.
Oh, that's okay.
Okay.
I just,
See, I'm still confused between the two differences sometimes. That's a lot of stuff. Really?
not again.
There's a fan.
Is the projector not operating?
Yeah, it always, I always turn it off instead of turning it on.
I think that's at least like.
It might just be that maybe it times out or something. I don't know.
Yeah,
It might not be anything you're doing.
but I'm not sure why it would be on
One cat is equal.
when I come in here.
I don't believe it's on because if you would tell if it was, it'd be making noise. So, yeah.
No, that's like a silent.
It's like silent mode. Yeah.
Yeah, but there's only light, so you can't see the light.
I would assume they have some sort of timer on it. Where if it's
Could be,
not
yeah.
used.
All right, so let's work through this together here. So we've got a fan. Q equals 20,000 CFM. Static pressure. This is an abbreviation, a conventional abbreviation for pressure. Inches of water gauge. When you talk about inches of water, it's almost always a gauge pressure, so it's relative to atmospheric pressure. Let's see, we've got a fan speed. Turning 500 RPM, and brake horsepower equals 18. And let's see, our friction. So our system is designed for 0.1 inches of water per 100 feet of duct. So this gives us the ability to use the ductilator to find out the size of the duct and get its velocity. What did you get for the duct diameter?
44 inches.
Equals 24 inches.
44.
44. Yeah, I know it's a big duct. It's a really big duct. So we go to the blue area, and we line up 20,000. Oh, I'm on the SI side. So 20,000 CFM is on the outer rim, and we line that up with 0.1. And then we look at the round duct, and it looks like 44, 43 and a half, 44. That's really big, that's a really big duct. But it's, you know, a really big building, that's
It's like
you might
over
have.
3.5 feet in diameter.
Yeah, you can get in there and crouch down inside of it. And, huh?
So that's big enough to hold Bruce Willis.
The whole Bruce Willis.
Sorry, I heard.
I don't know why you're saying that. Maybe it just reminded me of something totally, practically irrelevant, but there's a movie, I don't think it's Bruce Willis, but I think it is one of the Men in Black movies, but they're driving in a tunnel at high speed. I think they're chasing somebody, and they go up the wall and they drive upside down. Have you seen that?
Absolutely.
Huh?
That is Men in Black.
It is Men in Black. Yeah, they're driving at high speed upside down, and the question is that possible with the laws of physics? And I used that example in a class I used to teach in IAS called How Things Work. It was like physics for non-engineers. But I used that example, and we watched the video of it to show that yes, indeed, you can, in theory, get up to a high enough speed where the lift developed by the car will actually hold you up, and you can drive upside down. But you have to be going really, really fast. I can't remember how fast, but it illustrates the concept of lift. And of course, when you're racing at high speed, you use a spoiler to deflect air, so it holds the vehicle down. Otherwise, you can fly. You can lose control of the vehicle at high speed. Okay, but it's totally irrelevant. Okay, so what's the velocity? We go over to the red, and velocity at 20,000 CFM, and I believe it's around 1900. Did you get 1900?
Mhm.
Yeah, yeah, it's about 1900 feet per minute. So then B, velocity head, how do we calculate that?
Velocity over 4,005.
Right. Velocity over 4,005 squared, and just remember feet per minute goes in there, and out comes inches of water. So we put in 1900. And we get, I don't remember, 0.2? 0.22 maybe? Yeah, 0.225. On these larger systems where you start to build up static pressure, the velocity head becomes insignificant, and sometimes it's ignored in a big system like this. It's just not a lot. And what is the fan efficiency? How do we calculate fan efficiency?
Horsepower over brake horsepower.
So the air horsepower over the brake horsepower. And Our brake horsepower is the input, the fan is 18. How do we get the air horsepower?
Be the CFM times speed per, or times the pressure loss divided by 60.
Yeah.
Yes.
Right? And the total pressure, or PT, is static plus the velocity. And the static is given to us as 3. And we calculate the velocity head is 0.225, so 3.225. So we can come over here, 3.225. And Q is 20,000. And this gives us, let's see, I think it's about 10, if I remember. Okay, so that's the actual energy going into the air. Okay, but we're delivering the shaft. The shaft that's turning the fan is operating at 18 horsepower. So that means our efficiency, the fan efficiency, is 10.15 divided by 18. Right? Or 0.56. 0.56 for our fan efficiency. And then, then a motor is going to be driving the shaft. Motors are typically around 0.9. So if we wanted to find the motor horsepower or the motor efficiency would be 18 divided by 0.9. Roughly. We could even look up the efficiency for a standard motor using, there were tables given in one of the earlier chapters when you're calculating the heat generated by the motor. But we don't have to worry about that here. Okay? So then in number 2, we're going to change the flow rates. Something happens, somebody does something to cause the CFM to increase. And well, actually, we can't just, we're going to have to make adjustments. We're going to have to alter the fan in some way to get 28,000 CFM. And probably will increase the speed, but we could also increase the diameter of the fan. If the cage is big enough that we can put a larger diameter rotor, we might do that. But those are the 2 variables that we can usually vary with not a whole lot of trouble. It's the impeller size and the speed of rotation. And this is where our affinity equations come in. Let's see, we have the fan speed is directly proportional to the flow rate. That's the easy one. I think then pressure is so P2 over P1 is that right? I can't remember these. I have to look them up myself. I don't use them that often.
I think it's RPM instead of flow rate.
Oh, the R. may not have this
No,
right.
no, no. Oh, yeah.
Two. Yeah. It could also be N2 over N1 squared, since,
That makes sense.
yeah, and then we have, the work, power. So we could, we could also swap out the Q's with N's. That would be fine. Okay, so what speed? So speed is N. So we want to find the new speed, and we're going up to 28,000 CFM from our design. CFM is 20,000. With N1 is 500 RPM. So let's see what we get. 28 divided by 20 times 500 is 700. RPM, and then for the brake horsepower, well, I can use RPM, or I can use Q, and we'll just stay with Q since that's what we wrote the equation down as. So BHP2 equals BHP1, and 28,000 over 20,000 cubed, right? So 28 divided by 20 cubed times 18. Gives us 49. Not a lot bigger, going to be a bigger motor. And then what else? So the brake horsepower and static pressure. So the static pressure equals P1, and that varies with the square. Static pressure initially was 3. So that is squared divided by 20 squared times 3. 5.8, 5.9, 5.88. Okay, so there's a example using the affinity laws. Okay, got all that?
Yes.
All right, well, I want to switch this back now to water distribution, and I had some examples that I passed up last time, a couple of examples to work with you, and well, I have a couple of extras here. If you need anybody need a sheet from last time that has the water distribution examples? Now the first one, I need to work manually on the board here. And the second one I have worked out on my slides, because that one requires drawing on the graph. So let's pull that up, see what we have here.
Oh, for the air distribution.
Okay, so we have water at 140 degrees. So specific gravity is 0.99 at that temperature. And we're pumping it from a tank through 700 feet of 4-inch Schedule 40 steel pipe. We're lifting at 50 feet and discharging it at atmospheric pressure, or the inlet is atmospheric pressure, the outlet is 15.3 psi-G. So it's 15.3 psi higher than atmospheric. The line has some fittings, so we've got 6 standard right angle elbows, 1 gate valve, and 1 swing check valve, flanged pipe. And the system is designed for a constant pressure drop of 2.5 feet of water per 100 feet. So this is in line with the ASHRAE standards for energy efficient pumping. And I want to answer some questions here. What is the required pump head to push the water through this system? So what we need to do here, we need to find our losses, our head losses for the pipe and for the fittings. And I'm going to reference the tables that we have in the notes. Well, let's look at the fittings first. And we go down to, there's this table here, K factors for threaded pipe fittings, and then thread for flange pipe fittings. And we have, our pipe size is, so we've got 4-inch Schedule 40 pipe. So for a 4-inch pipe, nominal pipe diameter, flanged welded fittings, we're going to be on this line here, 4-inch. So for our right angle elbows, so 0.31. So I have 6 right angle standard elbows. So that is, each elbow is 0.31 is our K factor. And we have 6 of them. So 6 times 0.31 is 1.86 for our elbows. Then we have 1 open gate valve. So we come over here and we look for a gate valve. It's really hard to see horizontal here. Gate valve. So that would be there, 0.16, is that? Yes, the gate valve is 0.16, which is called valve. Okay, so our gate valve is 0.16 times 1 equals 6. And then we have one swing check valve. And that swing check valve is 2.0. And there's just one room. And we would do this for each section of the pipeline that is at a particular velocity, because we have to multiply these by the velocity head to get the loss. But because we only have one straight through pipe run here, there's just a constant velocity all the way through, so we can just sum these and then make one loss calculation. So we sum these, the sum of the K's is 4.02. And then for the loss due to the fittings, this is the friction head loss from the fittings, is the sum of the K. And velocity head, which is v squared over 2g. So multiply 4.02, and our velocity given?
I don't think so.
How do we find out our velocity?
Do we have to do Bernoulli's to find it?
Yeah, well, yes, but the easy way to do this is to go to a, we either can use the graphs that are in the chapter for head loss, types of various size for copper and steel, or my preferred approach is to use tables for the particular pipe that we're using. And this is a steel pipe, so if you go into the notes here on page 2, it says there's a link to tables. So here's for steel pipe. So I can go to steel pipe, schedule 40, and go to my nominal pipe size, which is 4 inches. There's 1 inch. Bring out 4 inches. So here's 4-inch pipe, and then it gives me all the information that I need. You know, if I know one of these other parameters. We said that the design pressure loss was what, 2.5 feet of water per 100 feet of pipe. So I come down my 4-inch pipe, so I come over to the pressure drop column. Here's feet of water per 100 feet of pipe, and I go down to my design target of 2.5, and this is really nice because now it's going to tell me how much water I can push through this pipe to maintain that pressure loss. So the relevant numbers here, the flow rate in the GPM is there, and the velocity will be 5.2 feet per second. You know, I like 4 well, 4 feet per second is one we're kind of moving towards, but 5.2 is okay. 4 to 6, I think we're good for an HVAC system. So our velocity is 5.2 feet per second. And we're going to be pushing through 206 GPM of water. Under those conditions. Okay, you see how we did that? Now you can get this off the graphs in the book. It's hard to read the graphs kind of. It's nice because it has all the numbers there on the graphs, but I prefer to use tables. Okay, so we can just now plug this in. Our velocity is 5.2 feet per second, 2 times 32.2 feet per second squared. So this is going to be squared. And you can see that's going to give us feet. It's going to give us feet of water because this is going to come out in units of head. And that is 1.688 feet. So that's my loss due to the fittings alone. Just take all the K, sum of the K factors, multiply by the velocity of head, and just make a note of that here. HF from the fittings is 1.688 feet.
So we have to do the major loss as well for the length of pipe.
Yes. Yeah. So HF for the straight pipe, or I guess we can just put pipe, is just the sum of just the total length of the pipe. So we go back to 700 feet of pipe. So we have 700 feet of pipe. So the fitting loss is pretty insignificant compared to our total length of pipe. Okay, and let's see, so what else do we need? We need to know what our elevation head change is. So usually I just make the inlet 0, or make one, either the inlet or the outlet 0, and the other is relative to it. To me, it's just easier to make the inlet at 0, and then the outlet elevation is relative to the inlet elevation. So we're going to climb up 50 feet. So Z2 is 50 feet. And then P1 is atmospheric pressure, which in gauge terms is 0. And then P2 is 15.3 psi G. So we're going to gain 15.3 psi of pressure. Yes?
So for the straight pipe loss, shouldn't that 700 be multiplied by the 2.5 feet per 100 feet of loss? So it says a constant pressure drop of 2.5 feet per 100 feet, and it's 700 feet of pipe. So should that number be smaller?
Yeah, thank you. Stupid error. It's not 700 feet of loss. That's the length of our pipe. We have to calculate that. So our because we're dropping 2.5 feet per is 0.5, 17.5. $700 feet. Yeah, you get a lot of pressure. You get a really big pump, big motor. Okay, so 17.5 feet. Yeah, this is, and sometimes I make the mistake of forgetting the 100. That, be careful. Don't forget to divide by 100. I do that a lot, and I've been called out for it too by people checking my work. Oh, you forgot to divide. This is another reason why it's important to have your work, have other people look at your calculations. Okay, so now we're ready to apply the Bernoulli equation. So we're going to use the extended Bernoulli equation where we take the friction loss into account in the pipe head. So our extended Bernoulli equation says that the pump head plus our velocity head going in plus our elevation head going in plus our pressure head going in. So that's all of our energy going in head expressed as head is equal to what's coming out. So everything coming out, velocity head out plus pressure head out plus elevation head out plus the friction, total friction. Okay, so we're looking for pump head. Solve this for pump head. Pressure, elevation, velocity. Plus friction. And that's going to be our pipe friction plus our fitting friction. Right? Okay, so if we're going to express this in terms of pressure, so our pressure out, we've got pressure out minus pressure in, professor out minus professor in. Time to think about retiring here. So this is going to be P2 minus P1 over the specific weight. So that deals with our pressure change. And our, and this is easy because it's just Z2 minus Z1 per feet. And then our velocity head change in velocity head. And then our friction okay. So now we just plug in. What do we do about the velocity term? What would you think?
Did we set it to 0 before the pump?
Well, the velocity, pumps do not really change the velocity unless the pipe size changes. And sometimes it does. Sometimes our outlet pipe size will be different from the inlet pipe size, and that will change the velocity. But usually, this is insignificant. Or if there is a change, even with a change in pipe size, this number tends to be really small compared to the other ones. So typically it's ignored unless we have some specific reason, significant change in pipe size, diverging pipes. Yeah, often if it's between two tanks, the velocity is 0 at the ends anyway. So there's no change in velocity if there's tanks on both ends. The other terms, of course, we do need to take into account. So let's see, we've got everything in there. Use this. All right, so our HA then is going to be the pressure, the difference in pressure, P2, we come out at 30 psi. Or was it 15? What is
15.3
it's 15.3. Minus 0. Or, you know, if you preferred to work with absolute pressure, like you really wanted to, you know, avoid using gauge. Usually in pipe work we use gauge pressure, but you would just add 14.7, so this would be 30 minus, and then the inlet would be atmospheric of 14.7. So you can use either one of those. This would be gauge or absolute. But since we're given the values in absolute, and that tends to be the easiest to work with because it makes usually one of the pressure, the atmospheric pressure, is just 0. So it's kind of nice to work with that. So we've got 15 minus 0. And the units are pound force per square inch. And then we divide by specific weight. And this is going to get us to a unit in fixing head, feet. And what is the specific weight of water well, this is the nice thing about the English system of units is that specific weight and density are the same number. So the magnitudes are the same. So the density of water in standard condition, 62.4 pound mass per cubic feet, and the specific weight is also 62.4, but pound force per cubic feet. Now, strictly speaking, I would need to multiply this by 0.99. I didn't do that here, but so this is going to be a little bit less than 62.4 at that temperature, 140 degrees. But I'm going to just use 62.4. So if we divide by 62.4, pound force per cubic feet, and that's going to require a unit conversion from inches, so 144 square inches per square foot. And now let's make sure that comes out in feet. We want feet. And pound force cancels, square inches cancel, and you can see this will be feet. So this is our pressure change in units of feet. Okay, so that's the pressure, and then the elevation side is just Z2 50 minus 0, and that's already in feet, so we don't have to do anything with that. And then the velocity term is 0, no change in velocity. And now we just add our losses from friction. So our friction loss from straight pipe is 17.5. And then our fitting loss is 1.688 feet. And when we sum that all that mess up, we get about 105. Feet. And the pressure doesn't really add much. This term is pretty small. This is 2 feet. This is the dominant. I mean, most of our work is going to lift the liquid to cover that 50 feet. And then the friction, that adds a bit as well. But the total is 105 feet. And now, since we have our HA, our pump head, we can calculate what our, so that's A. We just answered A. What is the rate at which the pump adds energy? So then the rate at which the pump adds energy, that's going to be the water horsepower or hydraulic horsepower, so WHP. And we can use, very similar to what we did with air, the total pressure times the flow rate. But we need to multiply by the specific gravity when it's different from 62.4, when we're at a different temperature from. It's not going to make a huge difference because it's 0.99, but we'll stick it in there since it's in the formula. And over 3956 to get to horsepower. So this is going to be 105 feet times, and this one's GPM, so this is feet, and that's GPM for water. And that's really nice because we don't have to convert gallons and cubic feet and stuff like that. And then 0.99 for specific gravity over 3956, and we find that we've got a pump. We're going to add energy to that water at the rate of 5.41 horsepower. Okay. So water horsepower. So comparable to air horsepower, dealing with air. And then our brake horsepower, so 5.41. Shoot, I'm running out of time. I haven't got today's stuff yet. And so then our brake, so pump efficiency is 0.8. Okay, so brake horsepower is water horsepower divided by the pump efficiency, or 5.41 horsepower divided by 0.8 gives us 6.77 horsepower. And then here's where we need to be careful. We need to do this with our fan as well. Don't just stop and say, oh, I need a 6.77 horsepower motor, because motors don't come in that size. You have to go to the standard size, and that is a little table in the notes that give you the standard horsepower sizes. And the next one up will be 7.5. So we want to specify a 7.5 horsepower standard motor. Okay? And it gives us a little wiggle room. And so 7.5 horsepower is our the motor size. And then if the motor efficiency is 0.9, what is the rate at which the motor is consuming electricity? So this would be, we're doing a financial analysis, which comes with every HVAC project. You're going to have to tell the owner or your client how much is it going to cost for you to operate this system. And so there's a cost analysis that you have to do with alongside the technical analysis. So in this case, we have, let's see, the electric power consumption. Well, let's come over here. Right, so our motor efficiency is going to be the output of the motor is brake horsepower And what goes in is electricity, electric power. And so we're solving for electric power. And our efficiency is 0.9. And since now we're going from mechanical to electrical, and electrical people do not use horsepower, oh my God, I used to teach a class to electrical engineers. Before we had ME, I taught electric power generation. Just kind of like a combination of, you know what you had with Professor Lee? It was like that class combined with thermal. You can imagine such a class. And the electrical engineers were just so annoyed by all the units that we use in mechanical. They're used to just using kilowatts, watts, kilowatt hours, joules. Now that's just it. And then you're throwing horsepower in, you know, and BTU, and of course we're used to that as Vietnamese, right? You just throw anything at us, except for slugs. Please don't give me slugs. That's like a peculiar fluid mechanics unit that I never see. I've never ever seen except in fluid mechanics textbook. Did you do slugs in fluid mechanics?
We did it in statics.
In statics? Yeah, slugs and poundle. Have you heard of poundle? It's some kind of mechanical unit. Dime? You know, there's all these weird units, and I think the worst is kilocalorie, which is actually equal to calorie with a big C, which is equal to 1,000 calories with a little c. Can you imagine? You know, so if you're doing nutrition, and I love to try, you know, when I use exercise equipment, I like to try to figure out how efficient my body is. So I'm looking at the power output from my exercise equipment. And so it's always giving me kilocalories, and I'm trying to always converting that to units that make sense. Yeah, so it's okay. But anyway, so we got horsepower. We need to go horsepower to. Actually, this one is worth memorizing, just because as mechanicals, when you work at the interface between mechanics and electrical, this is a unit that comes up a lot. It's 0.646 kilowatts in a horsepower, or 746 watts per horsepower. So that one is one that I still remember, even though my capacity to memorize is weakening, but also a convenient one is 1 horsepower is 550 foot-pound force per second. And then there's a BTU conversion I use a lot as well, but that one I tend to forget or I mess up. But anyway, we've got this one. Okay, so horsepower. So this is going to give us kilowatts, and 6.2 kilowatts is how much electricity, or the rate at which we're going to use electricity. And if we're paying, now see, somebody operating pumps in a industrial setting is probably paying, you're paying the electric rate is complicated. You've got an amount based on how much you're using, how many kilowatt hours you use, but then you've got a rate that's based on your maximum kilowatts. Now we won't worry about that. We'll just say 18 cents per kilowatt hour is so $0.18 per kilowatt hour. And we're operating this 4 months out of the year. About 4 months out of the year. Okay, so the best way to do this, because kilowatt hour is our electrical unit here, let's convert 4 months to hours. And it's worth remembering, when we, especially doing the economic side of the analysis here, is 1 year is equal to 8760 hours. So 4 months is 1/3 of a year. And that is, I don't know, I have to do the math here. 8760 divided by 3, so 2920 hours is how often how long we're using the pump per year. So 2920 hours, so 2920 hours per year. And that's going to give us money. This kilowatt cancels, kilowatt hour. So you have dollars per year, and you can see this is significant. So if you're somebody running an HVAC, big HVAC system, or a water flow system like this, it's not even that big of a system. 5 horsepower. I mean, there are hundreds of horsepower. That's a pretty steep price to pay for the electricity. It's probably a little expensive for electricity. All right, so I guess we can take a break now. You see how we did that? How we did the energy analysis? And it's what you did in fluid mechanics. It's a more practical application of it, perhaps. Problem 2. Let's see. That uses the pump curve, and that one involves making a pump curve. So it's like what we did in. There's an example in the air distribution notes. This is just a similar example using water where we see how we create the system curve? Now I think rather than go over this in class, because I do want to get into our next material, I'm going to make a video of this. Okay, I'll post it for you so you can look at it. And that way it'll be a seamless presentation. And yeah, so the next homework, there'll be problems related to water. This week was air. We've got water, and there may be some stuff, probably some stuff based on what I'm going to cover next, which is air, all air systems. We're going to try to finish with air today. We'll finish next time, I guess, because I won't scratch the surface today. But what I want to do in the rest of the time here, I want to touch on things that are so subparts of the HVAC system that involves air, which I think some of you are going to use in your projects. And that means cooling towers and energy recovery. Actually, I don't know if you're going to do energy recovery or not, but I was not planning to do energy recovery until I heard from our presenters. I can't remember who, but actually now building codes, especially in the city of Seattle, require that you do energy recovery in any beyond anything bigger than residential. You've got to have an energy recovery system. So energy recovery systems, I think that's going to be part of your design, just an expectation that you include that. And another important type of a system we're starting to see more application of is DOAS, Dedicated Outdoor Air System. So I want to talk about DOAS because I think that moving forward, we're going to see a lot more applications of DOAS. And DOAS usually includes energy recovery. So you kind of get cover two things with one topic. So we'll look at DOAS systems and how those work. And that's going to bring us back to psychrometric, using the psychrometric chart. So we'll do all that here in a minute. Let's take a break and stretch. All right. For today, the reading and the topic are focused on the system level aspect. We've been looking at the psychrometric part and pumps and air, and now going back to looking at the HVAC system as a whole. The reading for today, the chapter 9 and 10 in the book are weird. They're almost like little summaries of the ASHRAE handbook. Probably not all that useful, although it mentions important aspects of the overall design. Talks about the cooling towers, they even mention DOAS, and how you categorize all air HVAC systems. So my notes for today, which I have not posted yet, but I will do so today sometime. I am sorry I cannot create my modules in time for class. I just can't do it sometimes, and I'm really sorry. I'm frustrated by that, because ideally, in a class design, you would have all of this in Canvas by day one, or at least a week or two before it comes in class, and I just can't do it this year. I'm really struggling to keep up. But anyway, so it's coming. Just taking a little time here. But what I do here, this is all just writing stuff for the most part. So I want to just show you this and let you, you can download it and read it. But it talks about the overall design aspects. As an engineer, when you begin a project, you're going to have to develop a kind of a spreadsheet where the client says they want this, and you're going to think about, okay, well, we could do a centralized system or a decentralized system. That's your first decision point. Centralized or decentralized. Centralized means you've got a central plant that probably has a chiller, or maybe a big heat pump of some kind. And that's going to do all the cooling. It's going to make all the hot and cold that then gets sent out to everywhere that needs it. Or a decentralized system, where each space is going to have its own dedicated little system. The most extreme version of that would be like a window air conditioner, right? Everybody gets their own window air conditioner. The next step up would be what we call through-the-wall system, like a hotel room. Through the wall, that can often do heating and cooling. But when we get into commercial design or industrial design, probably the smallest scale decentralized would be a rooftop unit. So you put a box right over top of the room, or right over top of the building on the roof where you need heating and cooling, and you distribute those across the space. And then everything that you need is in that box. The refrigeration unit, the fan, and filters and things like that. So you're going to have to decide what centralized or decentralized. And you'll have to do a cost analysis. You're going to look at the client's budget. And this is going to be a result of a conversation with the client or the building owner that hired you. And there's some little links here that I would really urge you to explore, because it's nice to actually see what these things look like. So like a rooftop package unit. I think the engineering, this is an engineering mindset, I think. And I love their videos, because they go through what these are and actually show you, give you visual stimulus to see what these things look like. They're a little bit long. I think this one is about 12, 13. They tend to be 10, 12, 13 minutes. But they'll give you a sense of what these things look like. And then in a centralized system, there you probably have a chiller off somewhere, and then the hot and cold water gets sent out, and then there's usually a fan coil unit, which is a box that sits over each part of the building, classroom or space, where you're going to deposit warm or cold air. And again, there's a little thing here showing you, so here's the water coming in. Actually, I think that's the cold water and hot water, and the little box where there's a fan that will blow and give us the nice warmer, cool air. So this is just a discussion of the types of systems, and then you can further subdivide systems into centralized systems. Decentralized systems, what you get is what you get. I guess the main thing in a decentralized system is you can have ducted or unducted. You can have the big box that just sits, and then it drops the air right into the space. You don't need ducts going anywhere. But you can also have a decentralized system. Maybe the box is over on the other end of the building, and the air is brought over over here. But when you get to centralized systems, there are two subdivisions. There are two major subdivisions, and one is you can have a constant volume system, a constant air volume system, where the fan just moves air at a constant volume flow rate. So you need 20,000 CFM, you're going to get 20,000 CFM. And then there's variable air volume systems where you can actually, okay, so with the constant air volume system, you need 20,000, you design for 20,000 CFM, you're going to get 20,000 CFM. If you need it cooler or warmer, you change the temperature of that air. So constant volume, variable temperature. With a constant air volume system, you generally have constant temperature, variable volume. So you throttle the speed or the volume flow rate to meet the need at a given moment. And there's just some discussions here of what these look like. So here is the central system. Our cooling towers over here. Our chiller. Here we have two chilled water systems. Usually there's more than one because you have one that serves as a backup where it can be brought in when you need when the load is especially heavy. You can kick in and use both. I think here we have 3 or 4. There's quite a number of them. And they stage them based on what the load is. So anyway, we're talking about all air systems here. So these are systems where the heating and cooling comes from blowing air into the space. But that's not the only kind of a system. We can have all water systems. And those systems don't use fans and or forced air. They might have small fans that are local, but you don't move or have to specify and pay for big fans to move air around. You just make hot water or cold water somewhere, and you bring that hot water or cold water into the space, and you kind of let the air just, well, like the chilled beam system. You've got cold water up there flowing in tubes, in coils, and you can have active chilled beam or passive chilled beam. In a passive chilled beam, it just uses natural convection. The warm air rises up, and it comes into contact with the cold tubes. It cools, and then it drops down into the space, and then it warms and rises, and you just get this natural current of cool air up there, comes down, warms and rises, and that's a chill beam system. No fans, no forced convection, and very economical under certain conditions. Labs and classrooms are nice applications of them. But in an active chilled beam system, they actually will have a fan up there that it uses induction. It will suck air out of the room and kind of push it through. And it also will have, in an active system, you usually have a separate air conditioning system that brings a little bit of cool air in. So you mix the central air with the chilled beam air and then drop the air down in space. That gives you a little more cooling than you would have with passive system. But anyway, all water, we'll talk a little bit about that next, once we finish with the air. But air systems are much more complicated. We're seeing more water-based or hydronic systems because they tend to be more energy efficient, and water is a better heat transfer medium than air. And I think where we're especially seeing water become more common is radiant floor systems, where you move hot water under the floor. This is what 21 Acres has. You use a heat pump, like a air source or water source heat pump, and make hot water, and just you put a pipe grid under the floor, and the water, it's like a big coil, of wire and a water pipe, plastic tubes, and you rely on radiant heat transfer to pull that air up and into the space. And it's a nice way to heat because the floor is nice and warm. So you can tolerate lower air temperature when you're warm down at the floor. And there's all kinds of things. You know, the old-fashioned radiators. You go into like an old school, you know, it was built 50 years ago or 100 years ago, and there's these big radiators that have hot water flowing through them, and you touch them, ow! You know, really hot. But that's actually a great way of heating. And a lot of that is you're relying on natural convection and radiation for heating. And Europe still uses that. That's a very common form of heating there. Less so here. But we're starting to see that come back. Although now the designs are much more efficient than those old, those old radiators that kind of sit. But anyway, that would be a water-based system. And so I just talk a little bit about the two main types of air systems: the constant air volume system, and that's really what we've been looking at most of the time. This is the bread and butter HVAC system, kind of the most common, the traditional, where you got a space, you draw the return air out, mix in a little outdoor air, put the combination through, you filter it, heat, humidify, cool, dump it back in the room. And we've already analyzed that, right? We know how to do that. And but the key point here is this fan, you set it up and it just runs at a constant volume. It's moving 20,000, 15,000, 5,000 CFM, whatever you design for, that fan is giving you. And if you don't like that, then what we do is we change the temperature. And you do that by changing the temperature, or you do that by increasing or decreasing the cold water flow, going through the cooling coil, or you change the flow rate of refrigerant. This is a refrigerant coil. But the idea is to leave the volume flow the same. And that's a problem. These systems have really big problems, especially in hot, humid climates. And the reason is that in order to get the humidity down to a comfortable level, 50% or even 60%, you've got to overcool. You've got to drive the dry bulb temperature down so people are freezing to death. So people are really cold, but it's also using a lot of energy. And so generally, in that situation, what you end up doing is you overcool to get good humidity, and then you reheat. You warm the air to get the dry bulb back up. And we're really trying to move away from that. And some energy codes now are actually banning that, forbidding engineers from doing that. Because that's the easy solution. Using this kind of system, it's simple, it's cheap, quick and dirty, and oh, sorry, your air's too cold, we'll just put a little heating coil in here, and then you can play with that if you need. So the solution, and this is just this is showing how you can actually apply this system to multiple zones. And the idea is you deliver 55 degree. What you do in this situation is you look at your zones here, you do the heat transfer analysis as we've done, and you say, all right, who needs the most? Who needs the most cooling? Who needs the most heat? And you have to design the system for the zone that has the greatest demand. Now what's going to happen? Okay, zone C has the greatest demand for cooling. What's that going to do to zone A and B? It'll be cold, right? Keep the zone C people happy. These people are going to be wearing sweaters. So what do you have to do? Well, you got to keep these people happy. So reheat. So we're back to heating in the middle of the summer. It's 100 degrees outside, and you're heating the bloody air to get it. And again, this is not. We're trying to get away from this, but it is simple. And it tends to be what we teach because you can do this kind of a system rather easily without computers and complicated calculation. Now we can, if need be, we can add humidification in the wintertime. So sometimes we'll put in a little box, something that will humidify the air, especially really cold climate and dry in the winter. You want to moisten that air so we can add steam or hot water. And actually the hot water system is really nice because you can use that in the summertime. I don't know if you've ever been in a place where it's really hot and dry. You see this a lot like in Leavenworth or Spokane. Places in eastern Washington, like outdoor cafes, and they'll have these sprayers that are spraying water. Have you ever sat under those? It feels really nice. And what they're doing, it's a really hot day, maybe 95 degrees out, but it's really dry. So you miss this water, and that water evaporates. And when it evaporates, it actually draws heat out of the surrounding air and cools it, right? So that liquid water evaporates and then it cools all the air around it. It makes you feel nice. And so you can get that effect in the summertime with these systems by spraying water, not steam, but you would use water into the air, and that would cool it down without the need for refrigeration. When we use, actually I meant to use the water diagram. When we spray water, the device is called an air washer. You might see that term used, air washer, because it also kind of cleans the air. It's like washing out the air. Yeah. Okay, so to combat the problem of having to reheat and to not have good temperature control, variable air volume systems adjust the volume of the supply air in response to changes in cooling load without changing the temperature. So a lot of it kind of looks the same. The difference is, instead of just a reheat coil, there's a box called a VAV box, a variable air volume box. So you have a central system that's delivering 55-degree air typically. So here's your 55-degree air. Everybody gets 55-degree air. And then every space has a little box over top of the space that will change the volume flow rate based on the thermostat setting in the space. So it gives you local control with each zone having its own thermostat. What it looks like, you've probably seen these. You can see these hanging from ceilings in places. That's a variable air volume box. It's like a little miniature HVAC system, and it has a fan. I guess the main parts are it has a filter, a fan, and the fan is variable speed, so you can vary the speed based on how much air you need, and a damper to give you control over another control point over how much volume of air that you're getting. And what you do is, this is showing the damper, which you can open and close, and it's controlled by the temperature in the space and the differential pressure here between total and static. That difference is velocity. So by measuring, you probably did pitot tubes in, it's kind of like a pitot tube. It allows you to measure the velocity and to modulate, to use that signal, combine it with the temperature input in the controller, and then set that damper to give you the exact amount of air you need to meet set point. And so you put these around in all the spaces, the different zones, and then everybody's happy. So this is the kind of systems we design today. Probably when you go out, this is what, if you do HVAC design, commercial HVAC, this is going to be what you design, by and large. If you do an all-air system. There are some drawbacks to this kind of system. It's more complicated and costly, and there's some other things here, but yeah. A problem that you can have with these systems is, let's say you're in heating mode, it's really cold out, so you need a lot of heat, but suppose it's not so cold, you need less and less air, so you're reducing the volume, and suddenly you get to a point where you're not ventilating the space. So you can end up violating the code, the energy code, by not putting enough air in. The same in the summer, if you're cooling, if you can get to a point where you dial the volume down and then you go below the allowable for ventilation. These systems are set up not to allow that to happen. They automatically shut off. I think it's 60% of maximum, something like that, to make sure you have proper ventilation. And then you have this dead band in the middle here when you're in between full heating and cooling mode, and this is a mixed mode of operation. Car air conditioning systems kind of operate on the same basis because you can control the fan and you control how much air is coming out. But anyway, that's just an overview, broad overview of the kinds of systems. And then there is there's actually a presentation that goes with it. And this will have to wait until Monday, but we'll look at some components of the all-air system, exhaust air recovery, dedicated outdoor air system, and cooling towers. So we'll do that on Monday.
Thank you.
You all have a good weekend.